The discoveries of the James Webb Space Telescope have subverted the case for the huge explosion. The James Webb Space Telescope has quite recently conveyed an exhilarating revelation that is sending shock waves through the universe of material science. Through a single amazing picture, it has obliterated well-established discussions, leaving researchers paralyzed. The time of theory is over, as Webb's most recent catch is both outwardly enrapturing and a unique advantage that vows to upset our view of the real world. What red-hot discussion among researchers has this picture unequivocally finished? In what ways is the shocking picture caught by the James Webb Space Telescope rethinking our comprehension of the universe? Join us as we see why it's getting terrible as James Webb's finding closes the discussion in material science with a breaking blow. The principal issue with astronomy is that researchers can't come to an agreement about how old the universe is or how fast it is growing. This unanswered peculiarity has perplexed researchers across ages, and they are leading different examinations to find answers. Cosmology is the field of exploration that spotlights on understanding how the universe was made, the way things are assembled, and how it has changed over time and ultimately how it will end. This field has seen critical advancement in the past 100 years. The currently accepted cosmology model, the theory of the universe's origin, suggests that the universe has been extending from an exceptionally hot and thick beginning state for around 13.8 billion years. This development is estimated by the Hubble constant, which shows the speed at which the universe is growing. However, estimations of the Hubble constant are not clear. Estimations of the Hubble constant can be broadly classified into two groups: local estimations and early universe estimations. Local estimations involve the investigation of the galactic assemblages of the universe, for instance, Cepheid variable stars and type Ia supernovae, which act as standard candles to gauge the Hubble constant due to their luminosity. Astronomers can quantify how the universe's development influences the rates of these objects to determine their distances and hence compute the Hubble constant. The second group is the estimation of the early universe. Researchers use observations of the cosmic microwave background (CMB), the luminosity of the Big Bang, found in the 1960s. The CMB shows the microwave radiation of the early universe when it was only 380,000 years old. By measuring the tiny temperature and polarization fluctuations emitted by the CMB, cosmologists can establish the age of the universe and its rate of expansion. However, here's the issue: the results of these two methods don't connect. The outcome observed through local estimations affirms that the universe is growing quicker than what we gauge based on CMB data. Due to these differences, researchers have been endeavoring to uncover the explanation behind the results. As such, further research is being conducted to learn more about the secrets of the universe. As things stand, the difference in estimations shows that there is either new science we have hardly any familiarity with or mistakes in one or both methods of measurement. Because of the James Webb Space Telescope, we can see into the distant universe more clearly than ever before. The telescope can show the smallest and most distant components, planets, and systems we wouldn't have thought possible to see. Due to its capabilities, researchers naturally expected that data from the JWST would help us in accurately computing the Hubble constant. However, the first wave of data has strikingly made matters more complicated. They have given us new insights that are not consistent with what we assumed we knew. Might this data eventually lead to a new hypothesis and change how we contemplate space? If this is true, we might have to reassess how we interpret how the universe works. For example, we may find particles and forces that have never been noticed, or it could mean that dark energy, an unexplored world factor responsible for the speeding up expansion of our universe, should be reevaluated. Up to this point, the ways we think about space have evolved as we continue to discover new things. For instance, in 1965, when scientists discovered the cosmic microwave background radiation, it bolstered the theory of how things came to be. Before then, researchers believed that the universe was eternal and thus was continually expanding at a uniform rate. However, new evidence showed that was not true. Additionally, when we found out towards the end of the 1990s that the universe was constantly growing, we discovered dark energy and its impact on the universe's expansion. Subsequently, every time we learn something new, we question whether it fits into our current framework. If not, we concoct new ways to understand the universe better. To this end, The problem we are facing in cosmology today could lead to the discovery of the most profound answers about the universe. While the problem is challenging, it is also invigorating as it urges us to develop more advanced tools to explore space. This cosmological problem also unites the scientific community from various nations, as each researcher seeks to understand the universe. Above all, it shows that science is continually changing and evolving as we delve deeper into space. Alongside the Hubble strain, there is also a concern known as the S8 strain. This is related to the spatial distribution of matter in the universe. This can be used to draw a fundamental picture of the universe and recognize how it has evolved. Cosmologists refer to this phenomenon as clumpiness, as there are areas of space that have many galaxies closely packed together, while other regions are sparse. Researchers also use the cosmic microwave background, CMB, and luminosity from the beginning of the Big Bang. This light has been traveling for around 13.8 billion years, bearing news from the early universe. Through the CMB analysis, physicists can interpret how the universe was uneven in its infancy, which should match the observed clumpiness of the universe on a large scale. Yet, here's the trick. These results also don't align with the CMB's unevenness. The non-spherical gravity distribution model suggests that the matter distribution at the early stage of the universe was more homogeneous compared to what is observed using gravitational lensing. As such, we can infer that there is something else we are not considering in the explanation. This brings us back to the concept of dark matter. What exactly is dark matter, and how does it work? The truth is, this has yet to be answered. All hope is not lost, as the James Webb Space Telescope, JWST, is set to reclassify the field of cosmology with its exceptional high resolution and camera sensitivity. The telescope will examine early periods of the universe and explore the first galaxies and stars formed. This makes it possible to enhance our estimates of cosmic expansion and matter distribution. These fundamental questions will require precise observation and possibly new approaches from a theoretical perspective to solve. Whether the answer lies in discovering more about dark energy, finding entirely new physics, or even gaining a better understanding of dark matter's behavior, the implications will be far-reaching. Handling the secrets of the universe is like solving a billion-piece puzzle blindfolded. Researchers should be seen as thorough investigators, focused and fixated on solving these secrets. The latest endeavor, called Project Flamingo, is proof of NASA's increasing interest in scientific investigation. Utilizing one of the world's most highly acclaimed supercomputers, located at Durham University in England, Project Flamingo is a remarkable achievement in the realm of computational advancement. It costs more than 50 million hours of computer time and features 30,000 cycles and counting. The initiative highlights the academic community's goal to explore the universe thoroughly, significantly focusing on dark matter. Dark matter, the mysterious substance that neither emits, absorbs, nor reflects light, is thought to exist due to its gravitational effect on visible matter. Its elusive nature continues to intrigue researchers. However, Project Flamingo's approach is different from previous simulations. It includes all possible types of cosmic components, from galaxies with varying gas content to stars and black holes at the center of the universe. Through such a comprehensive method, a groundbreaking change in the portrayal of the universe was achieved from a fundamental landmark sketch. The inspiration behind ambitious endeavors like Project Flamingo is clear: to explain astronomical conflicts where the measurements seem defective and do not fit into the structure of the universe. This discrepancy in measurement suggests a fundamental misunderstanding in our current understanding of the universe's activities. If these measurements can be compared to musical classifications, they are like jazz and classical, each having its own method, albeit still related. Flamingo endeavors to integrate these unique perspectives and refine our individual view of the universe. Despite its complexity, the vast strain endured remains a testament to the fact that we have yet to address much of the mystery surrounding us. The universe appears reluctant to reveal its secrets, much like how each new data point and simulation model, like Flamingo, opens up an increasingly vast universe with new issues to address. It is a never-ending journey where each answer leads to more questions, unveiling a new layer of complexity. This demonstrates that our pursuit to unravel the universe's secrets is intricate and continually evolving. Since Edwin Hubble's brilliant discovery of the expanding universe in the mid-20th century, the speed of our understanding has been astonishingly quick. Past researchers have consistently made various discoveries about the dimensions of the universe, such as the Big Bang theory, dark matter, and dark energy. They have explored the galaxy by examining the cosmic microwave background, CMB, and meticulously recording the galaxy's positions and speeds at an ever-increasing level of precision. Each of these achievements is akin to finding another crucial piece of the enormous puzzle. This has led us to become more dedicated to learning and striving for a greater understanding of the universe. Indeed, the universe is shrouded in mystery, and it can be risky to uncover its truths too early. At each step, scientists present refined theories, updated models, and more, defining the demands for future advancements. The James Webb Space Telescope's findings are one such leap forward, reminding us of the vastness of our knowledge gap and pushing the limits of our curiosity. As researchers use the latest tools to solve problems, we continue to rewrite our understanding of the cosmos, revealing ever more profound truths about the universe and its origin.